Okay, so this is a tutorial video for how to use the standalone executable version of Sesame. So Sesame is a 1 and 2 dimensional drift diffusion Poisson solver, and it's specifically designed to model solar cells, in particular polycrystalline solar cells. It's a Python library, so you can use that library within your own Python scripting, or you can use this standalone GUI executable in a Windows environment, and so that's what I'll show you here in this video. You notice that the program takes a little while to get started. That's because it contains a full Python distribution inside of it. But here's a look at the main window, and so we have 3 tabs. The System tab here, which is used to define the system that you want to simulate. The Simulation tab sets the simulation parameters, and the Analysis tab allows you to plot and analyze the results. And so what I want to do here is just to quickly set up from scratch a simulation of a 2-dimensional n plus p junction with a grain boundary. And so what we have to do first is to define the grid that determines the discretization of our system. So Sesame uses finite differences on a rectilinear grid, and so to set up the grid, actually what we have to do is manually type in the grid coordinates and number of grid points. And what you notice is that we can have a non-uniform grid, so this is useful in the case where the solution varies more or less rapidly at certain points in space. You see that it's required to manually enter the grid like this in the form of beginning point, end point, and number of nodes in between the two. So that's a bit tedious, and it's something maybe we would like to automate in future versions. Once we have the grid, we want to define materials that comprise the system, and we first specify the location of each material region. And so here the coordinates are given by x along this direction, y along the vertical direction. And so this first material will occupy the space less than 0.1 e to the minus 4 centimeters in the x direction. And what we have here is the material parameters. So ND is the doping of donors, and so we'll choose this to have a relatively high doping density. No acceptors. Here is the effective density of states of conduction and valence band. Band gap, we can set this to be 2.4. Dielectric constant, epsilon, effective mass of electrons and holes. Electron and hole mobility. ET is the energy level of bulk defect recombination center relative to the intrinsic level. So typically they're most important near ET equals 0. Here is the lifetime of electrons and holes. So I'm just sort of picking numbers at random here. Electron affinity, radiative recombination constant, and Auger recombination constants of electrons and holes. So I specify all of these parameters and save the material here. And you can see when I save this first material, I get a depiction of the system as it's been defined so far, showing the grid in this gray region here is the material I just defined. So we save that. Let's make a new material for the p-type side of the junction. And so this will occupy the space greater than 0.1 e to the minus 4 centimeter. And in this case, we'll put in donor density of 1 to the 15. And all of the other parameters, most of the other parameters we can set to be the same. Notice I set the band gap to be slightly less, 1.5. Let's just pick kind of typical parameters for cadmium telluride here, and I save this material as well. And you see that gets depicted in the plot there. Okay, so let's move on and add a planar defect. And so this can be something like a surface or an internal grain boundary. So I choose new, and So we first have to specify the location of the defect, and so that's specified by the two endpoints. So let's say 0.1 e to the minus 4, 1.5 e to the minus 4. That's an xy of 0.1 of the first point. And the second position, let's make it something like this. Okay, and again, we have to determine to specify the energy level of the defect state, which is inside this planar defect. Again, relative to the intrinsic energy level, I'll just set it to be 0.2 eV above that. Defect density, this is in per centimeter squared because it's a planar defect, 1 e to the 14, so that's kind of a high defect density. And capture cross-section of electrons and holes. Again, I'm just sort of picking numbers somewhat at random here. And finally, the charge states of the defect. And so this would be something like the charge state when the quasi-Fermi level is above or below the energy level specified of the defect. So here, this is sort of like having a donor and acceptor defect state at this energy 0.2 above the intrinsic level. And so let's save that. And again, we see this depiction of a slightly tilted grain boundary in this N plus P junction here. Okay, in these regions here, I can define the illumination and absorption of the material. Let's go ahead and choose one sun illumination. For absorption, you can either specify the absorption depth, so let's say that it's 1E4. You can also specify absorption versus energy from a file in the same sort of format as used in SCAPS. Or you can set the generation rate manually, and maybe I'll talk about that later. So, okay, so we're done building the system, and we move on now to the simulation tab to set some more parameters of what kind of simulation we want to do on this system. So we can loop over either the applied voltage or some variable related to the generation if we use that manual generation rate. Let's just stick with voltages for now, and we need to specify the range of applied voltages that we would like to study. And so that's done using this linspace command from the NumPy library. We need to specify an output directory into which the results files will be saved. One thing that's important to keep in mind is that you want to make sure that you have permissions to write to whatever directory that you choose here. So here I just have a temporary directory that I save to. Output file name is the prefix of all the files that will be saved, and so let's say example. And notice that we can save either in gzip, which is a compressed Python format, or in .mat files, which is a MATLAB format, which you can use in MATLAB to analyze the solution. Now here are the boundary conditions. If we go back to the system, the way that this is constructed is on the left-hand side and on the right-hand side, these are contacts, electrical contacts, whereas on the top and bottom, these can either be hard wall boundary conditions or periodic boundary conditions. And all these boundary conditions are specified in this box here. So we can specify what kind of contact we have at x equals 0 on the left-hand side. It can either be an ohmic contact, Schottky contact, or what we call a neutral contact. Here I've chosen ohmic. In general, you also need to specify the recombination velocities of electrons and holes. And note that if you choose Schottky contact, you must then specify the metal work function. But for now, let's just choose ohmic for both contact at x equals 0, and also for the contact at x equals L. And so that's corresponding to the contact on the right-hand side of the system. And again, the transverse boundary conditions, that's corresponding to the boundary conditions associated with the top and bottom edges of this sample. And we can either have them be periodic, so that the system wraps around, connecting top and bottom, or hard wall. And here I just use periodic. Okay, so we have a lot of equations to solve. They're nonlinear, and so we need some technique for solving them. So we use the Newton-Raphson method, and there are some settings you can use to try to attain convergence more efficiently with this method. And some of these settings can be specified here. I would say typically I find that I can just leave most of these alone with the exception of generation ramp. And I'll talk about that in a second. Okay, so let's go ahead and try to run this simulation and see if we can get some results. Okay, and so what happens is that we first solve the equilibrium problem for the electrostatic potential. And okay, so that's done. And now we can move on and consider non-equilibrium problems. And what you notice is that the algorithm diverged rather quickly. And okay, the reason for this is actually that when we apply this one sun illumination on this system with a grain boundary with a high defect density, that's a very nonlinear system, and we're trying to push it a little too fast and too hard, and it's unable to find the solution. Now, the way that you get around that is to use this generation ramp flag here. And what that does is that reduces the magnitude of the illumination by, in this case, 7 orders of magnitude, and will slowly increase that illumination intensity by an order of magnitude at each step. And that's one way that you can start with a system that's just slightly out of equilibrium, where you have a much better chance of getting the solution, and slowly turn on the non-equilibrium driving force until you get to the type of system that you're interested in. And so you see that, okay, we're off to a decent start here, where we're able to begin to reach the self-consistent solution. And so we see that we found the self-consistent solution rather quickly. And now what we're going to do is we're going to slowly turn on the illumination, and that will enable us to get to the point that we're interested in. Once we have the self-consistent solution for 0 applied voltage, now we can crank up the applied voltage and get the solution and get the full JV curve that we're interested in. Okay, so we're going to let that run. It'll take a little while to crank up the intensity and then to turn on the voltage. While that's running, we can meanwhile look at some of the other capabilities in the analysis tab. So what's going to happen is that as different applied voltage solutions are found, those output files are going to populate this table here. We'll see those coming hopefully shortly. And we can, once we have the solutions, we can plot different aspects of the solution. And these two graphics here correspond to two-dimensional surface plots. And for example, you can plot all of the variables that are listed in this drop-down list here. So we have electron quasi-Fermi level, hole quasi-Fermi level, electrostatic potential, etc., things like that. This plotting on the right-hand side is a linear plot, and there are two options for making linear plots. One is loop values, right? So in this case, what we want to do is to plot some scalar versus the applied voltage values. And the sort of typical scalar you would plot is something like the total steady state current. Other options are the total recombination or the recombination associated with planar defects. The other option is to make one-dimensional cuts through this two-dimensional solution. And in this case, what we'll do, as we'll show shortly, is to specify the endpoints of the 1D cut line. And once we've specified those endpoints, we can plot things like a band diagram, or again, quasi-Fermi levels, recombination, electron current, things like that. Okay, so let's move back here and see how we're doing with the simulation. As I mentioned, we're cranking up the illumination intensity by an order of magnitude each time. So now we're 100 times smaller than the one sun illumination. And you can see that we're slowly converging each time. So this is the way it should work. Um, while we continue to wait here, let me just add one more comment. You notice that this takes a little bit of time to find the solution. And what I would say is that use of this GUI is fruitful in the context of doing small scale simulations or just playing around with systems in order to get a feel for how they respond or to develop some intuition about how they respond. But you see, this is probably too time consuming to do massive parameter sweeps. And in that case, the use of Sesame is much more effective if you use it in the context of a Python library. Because in that case, you can simply program massive parameter sweeps in Python scripts and send those to computing clusters, which can perform all the simulations simultaneously. And from that, you're able to get huge amounts of data in sort of one foul swoop. So that's sort of, I would say, the advantage of this platform is the ability to do cluster computing without having to pay lots of money for lots of licenses for the software. Okay, so here we can see that we finished the ramping up of the illumination intensity, and now we're starting to cycle the applied voltage. And indeed, we see that the solution files begin to populate this list here. So I can start to show you some of these plots that I was describing before. Here's a plot of the electrostatic potential for 0 applied volts. And you can see that here is the N side, here's the P side, and here you see the grain boundary distorts the electrostatic potential from the sort of standard NP junction. And so that's sort of what you would expect from the existence of this planar defect. We can also make plots of the electron current distribution. And so you'll see this rather complex plot showing the direction of electron flow with arrows, as well as the magnitude of electron flow given by the color coding there. Let's go back to the electrostatic potential. And let me show you an example of this linear plot that I was describing before, where we specify two endpoints of a one-dimensional cut of this two-dimensional solution. So let's say x equals 0, y equals 2.5 e to the minus 4, to x equals, say, 3 e to the minus 4, y is 2.5 e to the minus 4. And let's go ahead and plot the band diagram. And what I see here is a sort of prototypical band diagram of an NP junction under short circuit current conditions. Okay, so here is the conduction and valence band edges. Here's a heterojunction, right? So if you remember, the N side had a larger band gap than the P side. And the blue and red curves are the quasi-Fermi levels for electron and hole, respectively. And you can see the splitting of these quasi-Fermi levels as a result of the illumination. So this is kind of standard NP junction. And again, the cut is along this line here going through the junction. And what's interesting to do now is to consider a cut which crosses the grain boundary, let's say at y equals 1.75 and moving across this way, and see how it's different from the standard one-dimensional PN junction. So what I'm going to do is I'm going to change the y value to 1.75. And let me clear this plot so we know what that looks like. Clear and then replot it. And you can see the way in which this NP junction band diagram gets distorted by virtue of the fact of the presence of this grain boundary. So by staring at these plots long enough, you can start to develop some intuition for what this planar defect does. And you can see it has drastic impact on the electrostatics and the steady state configuration of the quasi-Fermi levels. I would say the reason why its impact is so dramatic is because the defect density associated with these planar defects is quite high, 1e to the 14, I think, in this case, per centimeter squared. And well, it's quite high because there's so many dislocations that occur at a grain boundary. And because of the requirement of electroneutrality of these potentially charged defects, and the fact that there are so many of these defects there, you have a strong modification of the electrostatics and the other properties of the solution. So it may not be so surprising that all of these charge defects, so many of them would distort the expected behavior of typical one-dimensional NP junction. Okay, so here we are. We're chugging away at the applied voltage sweep here. We're up to 0.7 volts. And okay, things seem to be going pretty well there. As I go ahead and consider other larger values of the applied voltage, I can make more plots of, for example, this 1D cut. And let's see, yeah. So you can see that as the applied voltage is increased, the potential difference between left-hand side and right-hand side decreases by virtue of the applied voltage, and the band diagrams change accordingly. Now we can clear this if we want to sort of clean it up and then take a look at this new band diagram here. Okay, let's see. What else can I describe? I'm just sort of waiting for this applied voltage sweep to finish up so I can finally show you a plot of the final JV curve. Okay, it looks like we're on our final applied voltage value here. So we'll let this thing finish up. We'll go ahead and clear this. We can take a look at, just for the fun of it, some of these other two-dimensional plots for this for the high forward bias voltage. And you can see, yeah, so things become like quite complex. Here's the whole current. And again, you see that the whole current is completely distorted from what you would expect in a simple N plus P junction. Here you see this very strong whole current at this particular point in the grain boundary in the bulk depletion region. So you can stare at these things long enough and you can actually start to get some intuition for how this grain boundary impacts the overall behavior of the junction. So let's looks like it's finally finished. Okay, so that's good. So let's go ahead and plot a scalar, namely the full steady state current versus the applied voltage. And there you have it. So notice the units of this milliamp per centimeter. So those are units of current density for a two-dimensional system. And here is 0. And so here is the short circuit current density. Open circuit voltage looks like we got something like 0.8. Okay. So you can sort of play with this till the cows come home. And for example, one thing you can do is you can add another grain boundary with sort of random endpoints. So let's say this. Okay. Energy minus 0.2. Density 1E12, let's say. Okay, and let's save that. So there's another grain boundary. And you can go ahead and restart the simulation and look at more plots like this. So I'm going to wrap up the video there and also point you to the presence of a number of example files that come with the distribution. So I think the standard directory for the distribution installation is in Program Files 64, Sesame. So notice this example subdirectory. There's 6 tutorials. The tutorials are described in the online documentation, and what you can do is you can open the tutorials, and it gives you some example sort of simulation configurations which you can use to sort of understand how some of this stuff works. So with that, I'll end, and thank you for your time.